Let us start our lecture. And I would like to recall you that a week ago, we considered the following problem. We considered a random walk as psi of n, where psi were independent, identically distributed random variables with expectation 0 and variance sigma squared. We continued this sequence by linearity to all t, and then we discussed so-called Skorokhod reflecting problem, and we denoted Skorokhod map by gamma, and we proved that there is a limit of these Skorokhod scalings, and the limit was gamma of Brownian motion at times t. Well, I wish to recall that gamma was a map from the space of continuous function to a space of continuous functions defined by the following formula. Gamma of f of t is equal to f of t minus minimum s in 0t f of s minimum 0. So this was Skorokhod map, and this Skorokhod map, so let me denote it by G, was a solution to the following problem. G of t is f of t plus L of t, where L is non-decreasing, G is non-negative, L is non-decreasing. You have this sum, and L may increase only when this function G hits 0. So I interpreted the Skorokhod map as the following. We have input f, it's like program of, it's some computer program, and it says go up or go down to a robot. So like here, so continuous function. And there is a wall at 0. And if robot hits the wall and wants to penetrate through the wall, then this function L pushes up in such a way that the robot is near the wall. So program says go down, robot stay near the wall, and when the program says go up, the robot goes up according to this program, and it go down until some moment when it hits the wall again, and if the program say go down, robot stays near the wall, and so on and so forth. Well, we proved that this Skorokhod problem has a unique solution, and this solution is given in the form by the following formula. Actually, this process is L. This function is L. And then we showed that gamma is continuous map from the space of continuous functions to the space of continuous functions. And it follows from Donsker's theorem and continuous mapping theorem that this Skorohod's reflection converge as processes in the space of continuous functions to some reflection of a Brownian motion. Today, I would like to discuss the following question. Okay, we have this reflection, but we have another reflection of a Brownian motion. So is it true that Skorokhod reflection of a Brownian motion has the same distribution as absolute value of Brownian motion? Well, this process is also called sometimes reflected Brownian motion. Well, actually, this is not absolute value of f of t, well, in general. So we don't have equality of these processes for all omega and for all t. So this is incorrect. So this is incorrect. But maybe the distributions are the same. And the answer is yes. And this is the first result for today, that the distribution of Skorokhod reflection of a Brownian motion and a Brownian motion have the same distribution. Well, let's prove this this result, and let me take concrete random walk. So assume that psi k are IID, and psi k are plus 1 or minus 1 with probability 1/2. So we consider x chi of n, this random walk. And well, expectation here is 0, variance is 1. We know that scalings of reflection of this random walk converge here, and scalings of Donsker scalings of this random walk of absolute value of this random walk converge to Brownian motion. Well, let me consider the sequence gamma of S psi n. Before we hit 0, increment of this random walk are plus 1 and minus 1 with probability 1/2. And now look what happens if this sequence hits 0. If psi k is plus 1, then the random walk reflects. But if the next psi is negative 1, so the program says go down, then you stay at the wall and you stay at the 0. If again the new increment is negative 1, then if psi k is negative 1, then you stay near the wall. If next psi is positive, then you go up, and so on and so forth. Sometimes you stay near the wall, and so on and so forth. It can be seen that this sequence is a Markov chain. What are the transition probabilities? Well, if you are above, then you go up and down with probability 1/2. So gamma of S, so let me write it like yn. Actually, this is a statement, so we get transition probabilities, but you have to check that the formula is true. So if I is positive, then you go up and down with probability 1/2 if I is natural number. If you stay at 0, then with probability 1/2 you go up, and with probability 1/2 you remain at 0. So py 0, 1 is equal to py 0, 0 is 1/2. Well, and now I wish to discuss, is it possible to use this random walk and construct from this random walk usual reflected random walk? And the answer, yes, it is. So what will I do? I will take this part, I will take this part and move it here and make this picture. And then I take this part, and then again I push it left and connect with the previous part. And I will see the following picture. So, okay, for example, this. So this part. Oh, I draw here, and this part immediately here. So I make this such procedure. I will write the formula later, but the statement is that after this connection, after this cutting and gluing excursions together, I will obtain a usual reflected random walk with transition probabilities. So the new random walk would be that 1/2 if I is positive, and with probability 1 you jump up from 0. And now so that is reflected random walk. Simple reflected is reflected random walk. Well, certainly I have to prove that this is really a Markov chain and so on and so forth, but it can be done by elementary methods. Now I wish to write a formula, mathematical formula that connect Z and Y. So at the beginning, so they're the same, and let me introduce. So if we consider this blue part, then I will say that, well, random walk Y moves in normal mode. And these parts near 0, I will call like critical mode. And I wish to calculate the number of steps in normal mode. So this is first step in normal mode. Oh, no. So this is first step, second, third, 4, 5, 6, 7. So you see, you go up. So this is the normal mode is continuing. 8, 9, and okay, this is critical mode. This is critical mode, and this is 10th step in normal mode. This is 11th step in normal mode, then critical mode, then 12th jump, 13, 14, 15, and so on and so forth. So what is the picture of that? say at instant 12. So this in 14th, this. So as we so z of n is equal to y at the instant when y makes nth jump in normal mode. So let me write like instant when y makes nth jump at the normal mode. It's easier to make pictures than to write formulas sometimes. uh, hmm. Well, but now let's try uh, to write some formulas. So let t normal n be okay. We take some number n, and we consider the number of steps in normal mode before n is sum k from 0 to n minus 1 indicator. So the normal mode means that, for example, here, 12 jumps. So it must be indicator that x, so previous step, xk is positive. No, previous step is positive, or previous step is 0, but now the value is positive, plus indicator that xk minus 1 is 0, and now I put sum from to from 1 probably. Yes, Igor? So what is the question?
From X or from Y?
From Y, certainly. Thanks. I didn't think. Yeah, sure. Y. From yes. Oh, okay. Now I think the formula is correct. And the number. What is the number of steps in critical mode? Well, you may write n minus t normal of n, or now look here. So, or we may write n minus number of jumps from 0 to 0. Oh, no, it's just number of jumps from 0 to 0. And let me recall you, when do this random walk jump 0? It jumps to 0 when the L, the compensation in Skorokhod problem, so this L increases, and ln is minus minimum k greater than 0 less than n s psi of k minimum 0. So we may write like this. And what is the instant when y makes n jump at the normal mode? So that n is y at the moment inverse. So let me denote. So instant when y makes n jump. So this is instant when this normal time hits level n. So this formula. So this is by definition. This is by definition. So infimum of k such that t normal of k is equal to n. Okay. So we have this equality, not equality in distribution, but just equality. Now let me copy this result. Okay, so this is important formula. And what do we know? We know that scaling of y converges in distribution to gamma of a Brownian motion, Skorokhod reflection of a Brownian motion. And well, why do I know this? Because y and t over square root of n is gamma of s psi n t over square root of n. And I know from Donsker scaling that s psi n t over square root of n converges to a Brownian motion. Well, and by the way, what is L? What is L? L and t, let's consider L and t over square root of n. L is a difference. L is a difference gamma s psi n t over square root of n and s n t over square root of n. Gamma is a continuous function in the space of gamma is continuous map from space of continuous function to continuous function. Well, identity map is continuous. So actually, we have convergence of pairs. Gamma s psi n t over square root of n. And oops, L n t over square root of n. Well, I may write like this, or I forgot, I have a formula, minus minimum of s and s over square root of n, minimum 0, s in s in 0t. Well, this is continuous map. So what is the limit of this? Gamma of w and minus minimum of w. And what what is the sequence z of nt over square root of n is gamma of s psi, and let me write here dot over square root of t. Oh, I have this. Okay. That taken at the instant this. So I have to write here t. I have to write here t divided by square root of n divided by square root of n, and so y. So let me write like n t normal inverse at the instant nt divided by n. So I multiplied and divided by the number n. I know that this converges here, and that's all. Now I wish to apply Skorokhod representation theorem, and to work not on certain probability space, but to work to work with copies that converge almost surely. So I know that there is a probability space and copies of S and L and W given on this particular probability space, such that, let me write n index n for copies. And this is a copy of a Brownian motion, such that we have almost sure convergence of this process to this process. And almost sure, I mean that in the space of continuous functions. So convergence in the space of continuous functions, say C0 infinity, means locally uniform convergence on each bounded set. And let me consider this process Z, which is function of y. Okay, t also depends on n on this particular probability space. And what was the formula for t normal? Not inverse, but just formula for t normal. So it was sum of indicators, and I know that, okay, I can write it like n minus t critical. And t critical is just L of n. So n minus L of n. So this t normal, and so let me write, and then I will think, is equal to n minus t critical of n. Well, all of these processes are copies, so I have to add here some index n, and probably I have to write here another index k. Okay, and normal time at the instant nt divided by n. Okay, this index that shows that there are copies is equal to nt over n minus t critical nt. I know that this is ln of nt divided by n. N is cancelled. And the next question, what is the limit of this? Please look here and maybe you may guess. Oh, no, not guess, prove. Please look here.
The second one goes to zero, yeah, because
Yes,
there we divide by square root of n.
yes, we divide here by square root of n, and convergence is a continuous process. And here we divide by n, so we have almost sure locally uniform convergence to just to t. And this convergence, locally uniform convergence. Oh, that's nice. Now, exercise from mathematical analysis. Maybe I have already given you this exercise that if Fn is a sequence of non-decreasing and non-negative functions such that Fn for every t, Fn of t converges to f of t, where f okay, let me formulate a simple version. 2t well, and functions fn of 0 is 0. Then sequence of inverses converges also to t locally uniformly. Uh, Actually, if Fn is non-decreasing, then inverses may be discontinuous. But nevertheless, you have locally uniform convergence. And now return here.
Excuse me. So here, where we have t normal to the minus one, it is actually tn. Yes.
Yes, this is
with, with the upper index here.
Yes, yeah. So now we have to consider the inverse of this. And again, small exercise that if f is non-decreasing, then inverse function, so not 1 divided by, but inverse function of a times f of bt is, let me write it like f of bt divided by a is inverse of f at the point at divided by b. And here a, b are positive and f is non-decreasing. So if f is strictly increasing and continuous, this is trivial, but for non-decreasing, you have to think a little bit. And inverse of this, so the simple corollary is that the inverse function of these functions, let me write here like dot. And here I should write probably dot instead of t. Inverse of this is,
Excuse me, in this
yes,
exercise, maybe in the left A, or wait, no, not A, B in the denominator.
here b.
From the right we have B, and from the left we don't have B.
B is here.
Okay, thank you.
Okay, so let me explain here that it is not a miracle, and assumes that f is strictly increasing and continuous. So if you solve equation f of bt, you take inverse of left and of the left and of the right sides. So t is inverse of f, over b. So you see this formula. But in our case, we have n here and there. So it's inverse of t normal at instant nt divided by n as in this formula, and what do we see? We see a sequence. So let me write like composition y of n dot over square root of n and t normal inverse of nt over n. And we know that this converges locally uniformly to a continuous function, and this converges locally uniformly to t for almost all omega. So again, a small exercise. If a sequence of functions converges locally uniformly to some function f, continuous function f, in the space of continuous functions, and if Gn converge to t or to g of t locally uniformly, where all of Gn are non-negative. Well, then and G is continuous. Sequence of compositions Fn and Gn converges to composition of the limit functions locally uniformly. And it follows from this exercise, so this is mathematical analysis, that this composition converge to composition of gamma of W and T, so to Skorokhod reflection of this. So what do we prove? So what do we prove? We proved that this sequence Zn, so Z and okay, we remember that sequence Zk has the same distribution as absolute value of the random walk. And we proved that there are some copies of Z such that the Donsker scalings converge almost surely in the space of continuous functions to Skorokhod reflection of a Brownian motion. On the other hand, this scaling has the same distribution as scaling of S psi, absolute value of the random walk. And we know from the continuous map theorem that this converges in distribution to absolute value of a Brownian motion. Well, because scalings of S is a Brownian motion, so and absolute value is continuous function, so we have this. Well, but this has the same distribution as this, so we have convergence in distribution to this process. What does it mean? This means that this process has the same distribution as this process, and the theorem is proved. Questions?
Can you go back to the previous slide? Yeah, so I already asked, but I want to clarify. So where we define Zn, yeah, with the upper script, it's Yn from this T normal, but this T normal is respective to
No.
normal.
It's with index
Yes,
n
yeah.
also. With index n also, yes.
Okay, thank you.
Yeah. So we work on new probability space where we have almost sure convergence. Well, sometimes it's not convenient to write these indexes n everywhere. Yes, and we proved that this sequence Zn proved here, but on the other hand, Zn has the same distribution as reflected random walk, not Skorokhod reflection, but usual reflection. Another question is this. We have convergence of pairs of this and this. And the question is there, and the first question, and the first coordinate is has the same distribution as absolute value of a Brownian motion. Is there some characterization of this part as a function of a Brownian motion? And the answer is yes. And the result was proved by Levy. And he proved a stronger result that Skorokhod reflection of a Brownian motion and this running minimum so that this pair of processes has the same distribution as absolute value of a Brownian motion and so-called local time of a Brownian motion. At 0, where the local time of a Brownian motion at 0 is equal to limit as epsilon goes to 0 of integral from 0 to t, indicator ws less than epsilon ds. So what do? We have a Brownian motion, maybe started from certain point, and we take a strip minus epsilon epsilon, so this time is t, and we calculate amount of time spent in this strip, and we divide by 2 epsilon the length of this strip and pass to a limit as epsilon goes to 0. And Levy proved that this limit exists almost surely, and he also proved that you have this equality. So this running minimum is a local time of this process. Oh, and by the way, you may also, yes, so since W of absolute value of W of S has the same distribution as this, then this process is the local time defined in the following sense, and of this process, Well, but be careful. Actually, this local time is not a continuous function of this coordinate. And this process also is not a continuous function of the first coordinate. That's why it is not. But it is continuous function of this W. Of this W. You may say, okay, but we have Brownian motion here. So is this local time a continuous function of this Brownian motion? The answer is no. The answer is no. Maybe it would be better to write here another symbol like B Brownian motion. So L0 is not so gamma of W, so it is not absolute value of W. So if you wish to say that this is a continuous function of some process, then you have to find W such that this absolute value of B is gamma of W. So if you find Wiener process Brownian motion W such that gamma of W is equal to absolute value of B, then you may say, well, this function is equal to minus minimum of W of S minimum 0 of this Brownian motion, not of this. So this is an important remark. And another question that I want to discuss is this. Let me consider absolute value of random walks, of random walk S, and the process L that was here was related to number of visits to 0. So I forget score-hod reflection and consider just reflected random walk. And my question is, what is the scaling limit of the number of visits to 0 of S? And is there any relation of the number of visits with this local time? And the answer is the following. The sequence of pairs. Okay, let me denote it by n of n is some k from 0 to n indicator s psi k is 0. N of nt divided by square root of n. And the result is this pair converge with absolute value converges to the pair Brownian motion and its local time at 0 and its local time at 0. Well, even without absolute values, you also have the convergence. By the way, the number of visits of reflected random walk and non-reflected random walk to 0 are the same. How to prove this theorem? Let us return to, I will give you only the idea. Let's consider this picture. Let us consider this picture and compare the number of visits of Z of so this is a picture of yn. Let us compare the number of visits of y to 0 and ln, the number of time spent in this critical mode. Well, they're different. For example, this is the first visit to 0. This is a second visit to 0. But no, so excuse me. But okay, well. Well, let's compare this and this. So first visit to 0, second, third. Well, I will not count this. So yk is 0, and so I will count. So visit means that previous was positive, was non-negative, and no. So I don't calculate this extra step. So when we arrive to 0, it's okay. When we arrive to 0, so I wish to calculate this. Okay, let's compare area of n and just arrivals to 0 from positive. Xk minus 1 is positive and xk is 0. So I count this point, this point, this point, this point. And by the way, these arrivals to 0 from positive, they have a relation to number of visits of this sequence z of n. So every arrival to 0 from positive side corresponds to arrival to 0 of this sequence, the Zn that we constructed. Well, the time for Z and for Y are different because Z is time change of Y, but let's compare these two. And so what is the difference? I may write that, so let me denote this by okay, n with tilde of n and ln, and ln is sum j from 1 to n of t xi of j, where xij is a number of red steps after j's visit, after j's visit to 0. So here n of n. So if you take some step n, then we count the number of red steps. The first arrival and we add 0. Then second arrival we add 2. Third arrival we arrive something. So this is greater than or equal, because if n is here, then we don't count this step. And we have another inequality, sum j from 1 to n of n, probably minus 1, xi j. Oh, this is question. What is the distribution? So xi j, xi is bad notation, epsilon, and epsilon r id. And what is the distribution of epsilon? Number of red steps. Vadim, what do you think?
So geometric.
Yes, geometric. And what is the probability that psi j is equal to k?
So it means that our process went up.
So it makes k minus 1
Yeah, so
steps
one
from
half
0 to 0
to the key.
and one step up. The last step is up. So the answer is
One half
1
to the
half
key.
to the power k minus 1 to the power k, let me think. So psi j is 0 with probability 1 half. Yeah, it's easier to, so 0 with probability 1 half. Psi is 1 with probability, so the first step is from 0 to 0, and the second step must be up. So 1 half squared, and so on. So, epsilon, sorry.
K plus 1.
Yes. So k is probability 1 over 2 to the power k plus 1, where k is greater than or equal to 0. So sometimes people consider geometric distribution that started from 0. Sometimes people consider geometric distribution that started from 1. Well, and okay, and the question is, what is expectation of psi, of epsilon?
Excuse me, can you please tell one more time what is epsilon?
Epsilon is a number, so green point is arrival to 0. And epsilon j is the number of red steps after j's arrival. For example, here epsilon 1 is 0. Epsilon 2 is epsilon 2 is 2. So this is second arrival and 2 steps. Epsilon 3 is 1. So 1 red step here.
Okay, thank you.
So what is the expectation of geometric distribution? Um, well,
Some derivative of
no.
1 over p.
Yes, 1 over p for geometric distributions that start from 1. And if it starts from 0, it's 1 over p minus 1. And now p is 1 half. So the answer is 1. So expectation of epsilon is 1. And well, by the law of large number, sum of epsilon j from 1 to n divided by n is 1. And I may write here square root of small n, and if I divide and multiply by square root of n, and let me think. Oh, no, I have to. Okay, I have to divide and multiply by n of n of n, square root of n. On the left-hand side, I divide by square root of n multiplied by n of n minus 1, n of n minus 1. And this converges to 1 almost surely. And I know that, well, again, we work on this setting of Skorokhod representation, and this converges to the local time. So these two, actually, ratio of these two goes to 1. So ratio of these two goes to 1, and this converges to a local time. So this must converge to a local time of the corresponding process at 0. Well, and then you have to construct from this Skorokhod reflection usual reflection, and then you say that, well, n of n is related to the number of visits of usual reflection to 0, and well, maybe certain calculations, and you will obtain this result. This result as a limit of, so the idea, you obtain almost sure convergence of copies in that are defined on the same probability space. Well, that's almost all for today. I wish to discuss one additional type of reflection, and let me call it oscillating random walk. And the picture is the following. So let psi k be ID like in Donsker theorem. And eta k also be independent, identically distributed with finite and positive expectation. And assume that all random variables are independent. And consider the following random walk. If it is positive, you use jumps psi. If it jumps to negative side, then you use jumps eta. Again, if you are on the positive side, then jumps of psi, then jumps of eta, and so on, and so forth. So we consider random walk y with transition probabilities. So in the jump has a distribution psi if you jump from positive number, well, non-negative number, and the distribution of a jump has distribution eta, if I is negative number, well, not necessarily. I and j are not necessarily integer numbers. Well, here I say that expectation of eta is positive, so theoretically eta may be negative. But it's easier to think to make pictures when etas are positive and to make some proofs when etas are positive. The question is, what is the scaling limit of y divided by square root of n? And the result is that Donsker scaling limit of this sequence is reflected Brownian motion. Okay, I assume that here is sigma. So let me write here, sigma is a reflected Brownian motion. I will give you only the idea of the proof, but we did a lot of work before when we glued together certain random walks. And the idea is this: I wish to obtain y or a copy of y as a function of s psi of n of this random walk and of s eta n. Well, for simplicity, let us assume that y0 is non-negative, that the first step is blue, and we assume that s eta is 0 and s eta of n is eta 1 plus eta n for positive n, and s psi of n is y0, so it starts at the same point as this random variable, and then you add xi1 plus xi2 plus xin, where this random variable is independent of xi and of eta, so everything is independent. Similarly to the case when we consider symmetric random walks, it's easier to make a picture of construction than to write formulas. So assume that we have this and this. So let me, okay, I will make a picture and then I will draw. So take this part, put here, and okay, this part I just glue here. Then I take this part and put it here. Then I take this part and put it here. So if you have y, then this green trajectory has the same distribution as this. And what is S eta? So I started from 0. So first jump, second jump, third jump, then these jumps, and so on. So if you have y, then you construct, then you may construct random walk S psi and S eta, and by the strong Markov property, they will be independent. And you may inverse this procedure. You may start from S psi and S eta, and if S psi cross 0, then you cut this part, and then you glue this part here until you enter positive side. Then you cut here, then you glue this part, and you cut this part when you are at the negative side, then you glue this one, and you continue this process. And now, how can we write this y in terms of constructed S psi and S eta? Y of n, well, I say blue part is like normal mode, and red part critical mode is S psi t normal n plus S eta t critical n. So normal is a number of blue steps until instant n, and t critical is number of red steps until moment n. Okay, we have this representation. So what do we know? Also, we know Donsker scaling limit, that we don't know Donsker's theorem, that scaling of this well, assume that sigma is 1 for simplicity. Otherwise, I need to write here sigma. Converges to a Brownian motion. What do we know about S eta? Well, I know that the law of large numbers, and I will write the law of large numbers in the corresponding form. So I will divide by square root of n. This converges almost surely to expectation of eta times t. You may tell me, okay, you have this for every t, but we discussed that we have locally uniform convergence of these processes to the linear process. And well, this process is non-random. So we have okay, so we have convergence of pairs of S eta square root of nt over square root of n to the pair Brownian motion and linear process. So let me denote it by A. AT. And we apply Skorokhod representation theorem, and we know that there are copies such that we have almost sure convergence to a Brownian motion, some Brownian motion. Well, I will not write tilde, and linear process AT. So I can consider the following deterministic problem. you have a pair of functions. So let me denote this function by f n of t and this function gn of t. So I fixed omega such that you have this. Fn converges locally uniformly to certain function f. Gn of t converges to at, and we make the following procedure of these two functions. Well, our functions are piecewise linear. So we cut and copy and glue together and obtain process of certain. And the question, what is the limit? What is the limit? And well, for all these copies, we also have this representation. So let me write here n. Well, I also have to add n here. Let me write nt here. Divide by square root of n. And divide by square root of n. Well, what do I know? That if I write here square root of n t divided by square root of n, then the limit will be linear function. So let me write square root of n here and square root of n there. And let me write n here, and so I multiply and divide. Well, let me rewrite. It would be better. So yn nt over square root of n is equal to s psi n times t normal n nt over n and divided by square root of n plus s eta square root of n times t critical n of nt divided by square root of n divided by square root of n. Okay. So if I denote this parameter by s, I know that this converges to a Brownian motion. Again, if I write that for this process, this converges to a linear process. So if somehow I prove existence of bounds for this, then I will know the limit of this process and of this process, and I need the following auxiliary result, that for every positive t, well, I need some bounds for this, but I need one notation. So let me denote by L of n the running minimum of y. of, no, not of y, of xi. And if we consider copies, then I write index n here, and now statement. For every k, probably, okay. So I don't consider copies, just L. For every k, we have the following inequality. L of k, L of t normal k is less than or equal to S eta t critical k, and is greater than or equal to and plus, excuse me, plus maximum of absolute value of xi j between 0 and m, and here S eta t critical k minus 1, and minus maximum of xi j. So let us discuss this inequality. I will not prove this lemma, so I leave it to you. And the proof is just looking at the picture and analyzing the picture. So, but you may make some rigorous calculations, use induction. So the picture. So what is before the first crossing 0? The running minimum of xi is 0. And you have 0 here. T critical of k is 0. This is 0, so 0 is greater than 0 minus something and less than 0 plus something. So that's okay. So what happens after the first crossing 0? The running minimum is equal to this distance. This distance, well, and this distance is less than this distance, and this distance is less than absolute value of maximum of all jumps. Okay. And well, then you add certain etas and so on and so forth. Then you have the second crossing 0. Please notice that this second crossing 0 may happen only when the new point is a point. So this green sequence has a minimum at this point. And now observe that this value is equal to running minimum of this green line, so minimum of the random walk, plus the sum of red. And this distance does not exceed the maximal jump of Xi. So if you add this maximal jump, you will be here, you will be in positive side, and value at the positive side is equal to sum of red plus sum of blue. And so sum of red is greater than or equal than sum of green with sign minus. So S eta and this L. So I don't prove this, so please cut random walks into pieces, glue together, and try to prove this result. And now, important corollary. I consider Skorokhod representation. I select copies that converge to Brownian motion. I write here n of t, and I divide by square root of n. And I know that the normal nt is that this part is less than or equal than nt. Okay, I consider copies everywhere. This converges to 0, almost surely. Okay, and Xi also with index n. Almost surely. Why? Because S Xi converge to a Brownian motion. So the scaling for this Xi is I divide by square root of n, and if this maximum value divided by square root of n does not converge to 0 almost surely, then the scaling limit of a random walk of discrete of this function cannot be a continuous process. So this goes to 0. This less than L of nt over square root of n, and this is less than or equal to ln n capital T. So I assume that T small is here over square root of n, and we know that this converges to running minimum of a Brownian motion. Let me write like LW of t. And this is finite number. So for every t in this guy is uniformly bounded. And now look here. S eta, let me multiply and divide by square root of n, t critical nt nt divided by square root of n minus 1 over square root of n over square root of n, and with index n, I know that this converges to AS. A times S, where A is positive constant almost everywhere, and locally uniformly. On the other side, this is bounded. This is bounded. I know this is bounded by this, and this converges here. So what does it mean? This means that this must be bounded. And this sequence converges to 0, so this sequence is bounded. So T critical of nt or square root of n, well, is less than or equal to t critical and t capital over square root of n, I know that this is bounded with probability 1. Hence, the first corollary, if you divide by n, then this converges to 0. So t critical of nt over n converges to 0 locally uniformly. Okay, this t critical depends on n with probability 1 as n goes to infinity. And if the time spent in critical mode converges to 0, then the time spent in normal mode converges to t. So t normal nt over n converges to t, okay, with index n with probability 1. And now we again return to our representation, knowing this information. This converges to t locally uniformly. This converges to a Brownian motion. Here we have composition of two functions. The first one converges locally uniformly to Brownian motion. The second one converges locally uniformly to t. So this function converges locally uniformly to Brownian motion. Now, the second term. Well, assume that that S eta that etas are positive for simplicity. And return back to this inequality. We know that the limit of this exists. This converges to 0. This converges to 0. So let me rewrite this equality once again. L t normal nt with index n over square root of n less than s eta t critical and t over square root of n plus of 1 s eta t critical of nt minus 1 divided by square root of n plus O small of 1. I know that this converges to running minimum of a Brownian motion locally uniformly. And I multiply here by square root of n, I divide here by square root of n. I know that this is bounded. I know that this is bounded. And what is the difference between right-hand side and left-hand side? Okay, the difference of right-hand side and left-hand side is this plus something small, and this term and different of these two terms doesn't exceed maximum of eta case where k is less than t critical and t over square root, and everything should be divided by square root of n. The question, is it true that this converges to 0?
Eta has the second moment, then it's true.
Yes, if eta has the second moment, that's true, but eta has the first moment. But this is also true. Let me explain you. If I consider this maximum eta k less than, well, certain constant times square root of n divided by square root of n. Well, I know that as eta square root of nt divided by square root of n converges to at, almost surely. So, almost surely and locally uniformly. So, each summand divided by square root of n must converge. Okay, so this implies that this converges to 0. Well, I have to be careful. Excuse me. Here I consider copies. And since we have this, then for every m, we have almost sure convergence. And I know that t critical of nt divided by square root of n is bounded. So there is a constant m such that t critical of nt is less than m times square root of n. So this term converges to 0. And we have almost sure convergence of this process to this. So left-hand side and right-hand side must converge to the same limit. And we recall the representation as psi t normal nt over square root of n plus s eta t critical of nt divided by square root of n. This converges to a running minimum of a Brownian motion. This converges to a Brownian motion locally uniformly. Well, I have to write everywhere index n because I work on a copy of with copies of original random walks. You have convergence, locally uniform convergence to W, to running minimum of W. So we have locally uniform convergence of these to the sum. So these converge here to this process. And this is gamma of W of t. So we proved that copies of the original random walk y, oscillating random walk y, converge to reflected Brownian motion. The theorem is proved. Maybe one small interpretation of this oscillating random walk. So this is work of Internet Shop. So Xi is, so you have a storage that has certain goods. And y is amount of goods in a storage. Well, but it may be virtually negative. What does it mean? You accept claims, so you say, I will sell you certain goods, but you really don't have them. And if you wish to sell more than you have on the storage, then you refill your storage by certain new random variables. So xi is refilling minus demand, so arrival minus departure in normal mode. So when you have positive number of goods in your storage, and these etas are refilling the storage in critical mode. And if xi are zero, mean that amount of goods in your storage is approximately Brownian motion, reflected Brownian motion, if you make this Donsker scaling. Okay, that's all for today. Thank you for your attention.